And in fact, 10 years from now, it may not be quite as important that a carbocation can rearrange, but it will be important that you follow directions. For your own success. So that's why when you ask me a question and I think it says that right there on page 3, that's why I'm kind of not interested in answering. All right, guys, let's get started. Should have already passed these out. Reactions, you have a purple handout. I'll split them in half so everybody can get one. Aromaticity. We'll pass the yellow one back maybe next time. Don't need it today. Any questions before we get started? Test will be returned on Friday. Any questions about the multi-week lab? If you don't have questions today, you can ask at the beginning of Thursday. Or Friday, everything should be clear. Or let me put it this way, everything that you should need to know is there. If there's anything that's not clear, please ask. Okay, you have a one I sent by email, aromaticity warm-up. I want to make some good progress today, some things that are going to be pretty straightforward, just kind of list information I'm going to try to go through pretty quickly, okay? And get us to the point where we can start working some problems and doing some stuff, okay? So let me kind of go through this. Hopefully by the end you'll be able to come back and answer these on the warm-up page like usual. Hopefully you've already been kind of working on those terms, aromatic, anti-aromatic, planar, non-planar. We mentioned this, number of drugs have aromatic rings. Aromatic's very important. We'll look at what's called heteroaromatics, or aromatic rings that contain heteroatom like nitrogen, pyrrole ring, and lipitor. So basically some reference. Intro to benzene and aromaticity. I mentioned nomenclature, but I don't want to do that today. I don't think. We need to make some good progress on structures of aromatics. What was passed out today? Purple sheet. It was purple? Okay, I passed out the wrong one.
You don't have an orange one up there, do you?
Have a what one?
An orange one?
Orange one? No, I got it. Yellow one.
Pass out the orange one.
Did I say orange?
Orange, you haven't passed it out.
I don't think we have orange paper. I haven't. We've got a purple already?
We have a purple. Yeah, we have. It's right here.
We have a yellow already?
No, we had green and blue.
Okay, I didn't realize we had purple. Okay, now you got two purple. Okay, it's supposed to give you the yellow sheet. The yellow is sort of the outline of your aromatics. Basically, the first thing is the structure of benzene.
So do we need the purple at all?
Not today.
Okay.
That's actually reactions.
So we will need it later though.
Okay, purple's coming around. Intro to benzene. Benzene is a liquid boiling point about 80 degrees. Okay, it's a good solvent. Pretty darn good solvent. Problem is it's a carcinogen. And so it's pretty much outlawed. Industry doesn't use it. I don't use it anymore because when I used to use it, we used to make my elbow right here hurt. Muscle problems, etc. Bad stuff. Messes you up. It's unfortunate. Of course, lots of drugs contain benzene ring. You start putting substituents on there, and it's not as toxic. Okay, even you just put a methyl group on benzene, not as toxic. First isolated in 1825 from well fat that used to be burned in the street lamps. From that, some residue was distilled off, and they isolated a pure liquid that had a boiling point of 80 degrees, and they started studying it. They didn't know what they had. In fact, the double bond was not even proposed until the 1860s. Okay, but of course, 300 400 years ago, they could get a pure compound and say, hey, it seems to be a single substance. They didn't have a big idea about molecular structure. But they could tell purity. Review of structure, of course, all carbons are sp2. Okay, trigonal planar, 120-degree bond angles around each carbon. So it's a perfect hexagon as a result of that. Of course, if you look at each sp2, it's got three hybrids, what's left, a p orbital left over. What's each carbon making? Sigma bond to carbon, and sigma bond to H. Yes, there's an H on each carbon. 3 sigma bonds. It's also making a pi bond to carbon, and together this is what? Double bond to each carbon. Okay? So it's a perfectly symmetrical hexagon. If we just draw the sigma bonds, we can call that the sigma framework. Okay? Sigma framework, there's your geometry, trigonal planar. Everything's planar, 120-degree bond angles. What's missing on each carbon? The p orbital. Each carbon has a p orbital, and if this is flat on the board, each of these is coming out, and so you can have 6 of these going around. If I held 6 up here, there's 2, 4 more, and they're all coming out, and they're all overlapping, of course coming out this way and also going behind the board. Now if I turn it, I can draw it sort of like this. So the pi system is said to be perpendicular or orthogonal to the sigma framework. That's going to be called the pi framework. Of course, 1 electron in each. And then the question becomes, well, if you draw classical double bonds, 1 electron overlapping, pi bond there, 1 electron, pi bond here, and pi bond here. That would give this. Well, why not overlap instead there, there, and there? Why not do that instead? Give that. Which one's right? They're both right because you have continuous overlap. There's overlap all the way through there. Okay, and we get the idea of extended overlap, conjugation, and we know that these are really 2 isolated fake structures. These are resonance structures. Okay, they're both good. They're actually both wrong. The true structure would look more like at the very bottom. A lot of times people draw it with just a circle. That is, if you take a blend of the resonance structures, what's the bond order between carbons A and B? There it's 2, there it's 1. What's an average of that? Yeah, so we got a BO equals 1.5, really all the way around. It's delocalized bonding at its best. And so a lot of people just draw a circle. That's sort of like, what's a bond and a half? Bond and a half, bond and a half, bond and a half, bond and a half, etc. all the way around. That's supposed to be connected, right? And so instead of doing that, quick hand is just to say, okay, all the way around. I would not recommend drawing like that, though. That is overly simplistic. And when we start doing reactions, well, you can't do reactions with just a circle like that. You got to see the pi bond. Okay. Of course, showing it with the pi bonds that's kind of fake. It's called a localized view. Okay. Now I did that right here already. Bond lengths. Some evidence. What is some evidence for this? First off, all carbon-carbon bonds are the same length. It's 1.39 angstroms. Okay? Now, if it was double, single, double, single, double, single all the way around, well, a single is longer than a double. Standard double bond, alkene is 1.3. Standard single bond is 1.5. So if it was truly alternating double, single, double, it would be sort of short, long, short, long, short, long. But we know it's not. We know it's 1.39, which is essentially right between the two. Now this is probably rounded off, but it's not 1.4. So it's right between How do we know this? Well, something like X-ray crystallography, where you can actually see bond lengths, closest way you can come to seeing a compound. And so instead of this alternating, it's truly a perfect hexagon with equal bond lengths all the way around. Now, Kekulé, who was back in the 1800s, first started thinking about what's this liquid that comes from well oil that's been around for 20 or 30 years. Tried to basically advance the structure and came up with this common structure that we know today. By the way, in one of the handouts, there's some structures of what they originally thought benzene might be. Some of them sort of odd. What did they know way back then? They knew the percent carbon and hydrogen, so they could do that very early on. That's the main thing they knew. So they knew it was essentially C6H6, or some multiple though, because that's the empirical form. Maybe it's C12H12. Either way you go, it's got the same percentage. Kekulé actually tried to isolate these two different isomers. And guess what? He could not do it. This one he said, well, the double bond is going to be between the two bromines, and then we should also be able to get the double bond without. Not between the two bromines. Could he ever do it? No, because it's really not two different compounds. Right? It's really, these electrons are all the way around. It's the same thing. That's just two different ways to show it. I mentioned X-ray crystallography. Here's just an example of that. You don't see that much of that in the undergraduate curriculum. This is a compound we made in the research lab. We got X-ray, it was done at Emory. It contains 2 aromatic rings here. So this is an actual view of the compound. This is experimental data. And you can kind of see some of the 3D nature because we got these tetrahedral carbons here and here. What you see is that the ring is very planar. Because these p orbitals overlapping makes everything planar. But you also get bond lengths. And I'm not sure what I'm trying to highlight here. Yeah, the ones I kind of ticked there, they're all about 1.376, 1.38. They're all pretty darn similar. Okay? Now these are substituted rings, and so they may not be as exactly localized as benzene, which is sort of the granddaddy of all aromatics. Very, very delocalized, very symmetrically delocalized. If you start having substituents, it may make the electrons sort of perturb a little bit, yeah? And if you have like an electron withdrawing group, you're like, but still, you're not going to see like 1.3 and 1.5 for single double. You take a look at that. You really look at this a good bit and sort of have some questions about that, the way the rings are positioned. They're not both like this. One of them is actually turned a little bit in the crystal structure. Okay, so that's a little bit of a background. What is aromaticity? Our first definition will be it's an unusual stability as a result of full cyclic conjugation. Cyclic conjugation, complete, that is full loop. Cyclic conjugation. That's what we just said about benzene. Fully cyclic conjugated. Leads to an unusual stability. What type of stability are we talking about? First off, we have, I see B and C, but I don't see A. I think you got a hole punched out.
It's in aromaticity.
Oh yeah, no. I think you got a hole punched out right there. Did it?
No.
Did I just start with B?
No, you have A and B.
Just where? Oh, that was A?
Okay.
Well, let's, Let's don't worry about it.
Oh, there it is. It's all carbon bonds are the same length. It's like halfway through the page, under evidence for delocalization.
Okay, yes. So that takes us back to what are we looking at? What are we looking at? Evidence for delocalization. The first evidence is we can tell bond lengths from like X-ray crystallography. That's evidence, right? We're not just making this up. What is some other evidence? Well, we have unusual reactivity. You go to the lab and try to react these aromatics, you get unusual reactivity. For example, you try to react benzene with bromine, you say, hey, I got a pi bond. I'm going to do a transaddition of bromine to a pi bond. Well, guess what? It doesn't happen with benzene. It is not three alkenes. Okay, it does not react like this. Instead, you react with bromine. First off, it's very sluggish. Most alkenes react with bromine instantaneously. Remember when we brominated organic 1, it was almost like a titration. As soon as you added it, it reacted, right? Bromine much slower. Actually, you have to add a catalyst, usually like an iron catalyst. So, sluggish. And when it does react, you don't get addition. What do you get? You get a substitution reaction, where one of the H's is replaced with a bromine. You also produce HBr. That's the fate of the H and the other Br. So instead it reacts by substitution. Why? Well, guess it wants to maintain the aromaticity. That's the thermodynamic driving. We'll look at the mechanism. That's no longer aromatic. Is this fully cyclic conjugated? No. These two carbons no longer have p orbitals. You have conjugation here, this diene, but it's not fully cyclic conjugated anymore. And that's going to be less stable than the aromatic. And you typically are not going to want to make a less stable compound if it has an alternative pathway. We'll look at that mechanism, and guess what you did in lab last week? You did a substitution, right? You replaced an H, one or two H's of sulfanilamide with your halogen. Question?
Why doesn't it pull up more than one H from bromine?
Well, we're assuming one equivalent of Br2. If you used excess, you can put another bromine, do another substitution. I'm just using one equivalent in those two examples. We know alkenes react with like osmium tetroxide, KMNO4, alkene oxidation. Well, guess what? Benzene doesn't. It doesn't react. It doesn't do anything, at least not in this class. There's a very unique way to get it to react with one of these, but we're not going to get into that. But the basic discussion is it doesn't react. So we got some, it's not an alkene. It's more unusual. It's got its own reactivity. Those are some observations we make in lab. We can actually quantify this a little bit when we do heats of hydrogenation. Take an alkene, hydrogenate it to the alkane. It's an exothermic reaction because we're making two new sigma bonds. Yeah, we did this in organic 1. So you're going to release some heat, release 118 kJ per mole. If you take the diene, do the same thing, assuming excess here, you get the same product. You might think double the heat. It's not double. Double would be what, 236? Why is it not exactly double? Why is it not double? Conjugation, yes. Now if we hydrogenated this one, that would be more like double exactly. One alkene, two alkenes. What's the difference in these two? Conjugated. This is lower in energy than this one. Okay? So because it's conjugated, it doesn't contain quite as much energy to release. It sits at a lower just because of its nature. Okay, you put a third double bond in, get benzene, you might think this to continue to like increase, almost double again, or another times 3. What's 118 times 3? It's like 360,
Yeah.
350 or so. Well, look. Putting another pi bond, actually, which is more stable, top or bottom? Bottom is more stable. So putting another pi bond actually makes it more stable than that one. So that's odd. Why is that? Well, ultimately because now we've reached the magic benzene ring, which has a magic stability. Cyclic conjugation really lowers the stability. So if 118 times 3 is 354, the difference between 354 and 205 is 149. That 149 is often called the aromatic stability. So this is not just 3 alkenes. Question?
So in all of those reactions, you could say that the alkene is going from order to like disorder. Wouldn't you have to like add energy to that to make that happen? Why is it releasing energy?
Why, you're looking at entropy.
Yeah.
Well, the alkene is, you're talking about the system. Alkene plus hydrogen. So you bring in the hydrogen, and you're saying 2 molecules are going to 1. Yeah. Yeah, this is just thermodynamics. It's not an overall delta G, but this is just delta H. Yeah. I'm not looking at the entropy factor that you're bringing up. One other thing that we can mention here is that these can be hydrogenated with just like simple plain old carbon. To hydrogenate benzene, it's actually more difficult also. Even though it's exothermic, it's more difficult. You usually have to use something, a more active catalyst, sort of like rhodium or ruthenium. Those tend to be more active than like your standard palladium or platinum or nickel. You also tend to have to use pretty high pressure. That's not noted here. So it's reluctant to be hydrogenated. You can do this. You can convert benzene to cyclohexane. It's very reluctant to do it. And usually you don't do it. I mean, it's very rare. D almost got a whole bunch. What are some other evidence we have? Well, NMR. Remember your alkene region in NMR, proton is about 5 to 6. Aromatics, though, is 7 to 8. It's more downfield. So that can distinguish between maybe just an alkene. You know, if this was just 3 alkenes, these peaks should be 5 to 6. The fact that they're downfield tells us that they're not just alkenes. And we classify them as aromatics. Why is it more downfield? We talked about that a little bit, the anisotropic effect. There's a significant pi system here. That pi system actually acts to further de-shield the proton. There was sort of a graph where we had this type of thing going on. If you look back at the NMR packet. So what we're all getting at here is, what if I brought in a compound and said, hey, look at this clear liquid here, clear colorless liquid. Clear colorless, right? Y'all know clear is not a color, right? What color is cranberry juice? Clear red. All right. What color is orange juice? Clear orange? No, it's not clear orange. Clear describes turbidity. Okay. Water is clear and colorless usually.
Not ours.
Okay, good. Yeah. Yeah. Y'all ask about deionized water in the lab. We don't need to use deionized water. I usually say unless the water is brown coming out of the tap. Okay? If it's brown, we don't use it. It's organic chemistry. Don't fear the ions. Okay? If you do fear the ions, please explain why. All right. So So basically, if I had a liquid and said, okay, is this aromatic or not, how would you, what evidence would you collect on the compound? NMR. What else would you collect? You said reactivity, what would you do? You would,
Well, you could throw like osmium tetroxide.
see if it reacts with that very toxic osmium tetroxide, which by the way is on the, it's on the chemical weapons list. Very common, you can react it with bromine. Does it react by addition or does it react by substitution? IR looking for what? Like the aromatic signature? Possibly. Yeah.
Could you do like boiling point?
Well, what would you compare it to? Say it boiled at 160, what would that tell you? Yeah, I don't know how that's going to tell you if it's aromatic or not. I don't think unless you really got down into some detail in predicting. Okay. Our yellow, is it yellow?
Yeah.
Structure, yes, that tells us what we're doing. What are we doing? Structure, experimental evidence, bond links, reactivity, heat hydrogenation, H&R. Did we just do that?
Yep.
Okay. Number 3. Comparison of benzene to cyclobutadiene. Very stable. This guy over here, very unstable. This guy over here only exists at very low temperature, like minus 78 degrees, which is dry ice acetone temperature. If you let it warm up, it'll dimerize, and it'll convert to another structure. Doesn't sound happy. Why is this compound so unstable? Angle strain. Okay. That wants to be 120, but it's stuck in this 90-degree arrangement? Possibly. But I could show you something like this. That's actually very stable. That's more stable than this guy. And it's a cation. So what does this do to your bond strain theory? Goes a big hole in it? So this is even more angle strain, right? So it's not really angle strain. What else is it? Well, we need to explain. This is a classical aromaticity issue. This is called aromatic. This is going to be called anti-aromatic. Why is it known as anti-aromatic? First off, both are fully conjugated cyclic systems. Or fully cyclic conjugated systems, right? Fully cyclic conjugated? Is this fully cyclic conjugated?
Yeah.
That is, does every atom in the ring have a p orbital? Yes. So it is fully cyclic conjugated. So already we're having to modify our original definition. Because our original definition said aromaticity is an unusual stability as a result of full cyclic conjugation. Well, this is not an unusual stability. What this is unusual instability due to full cyclic conjugation. And that is known as what? Anti-aromatic. Okay? Both of these types are fully cyclic conjugated. We will have a third type as we go on. We will have a type called non-aromatic. Non-aromatic are your systems that are not fully cyclic conjugated. For example, that is non-aromatic. Is it fully cyclic conjugated? No, non-aromatic. What about ethanol? Is that fully cyclic conjugated? No. Ethanol's non-aromatic. Okay, to answer this, we're first going to have to do MO diagram. Get into that a little bit. MO diagrams, I don't do much in organic 1. Let's start by doing an MO diagram of butadiene. MO stands for molecular orbital. Everything we've done with me has been we stuck with atomic orbitals. Okay? Atomic orbitals. And we can draw that here. What do we have? Pi bond, 1 electron each overlapping. That's that pi bond. We also have it here. 1 electron each overlapping. We learned that there is overlap between the middle, right? That's conjugation. We can draw resonance and stuff, extended pi bonding. But these are still atomic orbitals. There's 4 atomic p orbitals I have there. A molecular orbital is where you combine all of your atomic orbitals and make a new orbital that is spread over the entire molecule. It's called a molecular orbital. It comes from combining your atomic orbitals. All this is based on math. And you can, there's like an acronym, mathematical combination of atomic orbitals or something like that. You can look it up on the wiki. How do we combine these? Well, we're not going to do it mathematically because I could not do it. We combine these basically different ways. These can be combined based on phase. Let me set this up so I can also do energy diagram. Let me do it like this at the bottom. Boom, boom, boom. I'm going to draw these at the beginning. As we go up, we won't draw the p orbitals. The best way for these to combine is all in the same phase. Denoted with positive. All combining in the same phase. And that's going to give us 1 MO. And we're going to have energy here. And this is 1 orbital. We'll come back and put some notes here. Is there another way to combine these? Maybe? Well, let me give you this. Now, I'm not going to draw the orbital anymore. What we're going to do now is just draw the sign and pretend like there's the 4 orbitals. It's just going to save us some ink and time. Another way is to go maybe plus, plus, minus, minus. And this is going to be another molecular orbital.
16 combinations.
Do it.
16 combinations.
No, I'm only going to get 4.
Okay, yeah, I see.
No. Okay. One thing we can look at this is, what does this molecular orbital look like? It looks like that. This becomes known that that's 1 molecular orbital. Okay? That's 1 MO with the relative energy here compared to the one above it. And this is going to be 1 MO. And how we're going to kind of classify this is, in this 1 MO, what type of interactions do you have between what used to be the p orbitals, the atomic orbitals? This is going to be called a bonding interaction. This is going to be called a bonding interaction. This is going to be called a bonding interaction. And we can classify this by saying, how many bonding interactions do we have? 3 bonding net. Those are the good interactions. How many interactions do we have up here? Bonding interactions. This is bonding. What is this?
2.
That's bonding. There's 2 orbitals overlapping the same phase. That's called bonding. That matters. Okay. But what is this here? That's anti-bonding. Okay? That's where the orbitals didn't like each other. And they cancel each other out. This is sort of like waves in the ocean. Waves can come together in a lake. They can come together and build a bigger wave. That's where they reinforce each other. This is sort of like reinforcement or bonding. Or can't waves come together out of phase and they can sort of cancel each other out and you go dead? You can also have like sound waves. Sound waves can go dead. Isn't that right? And that's how you can get like just sort of dead space in sound. So that's where the waves came together out of phase and they canceled each other out. That's sort of what happened here. So we have, they call it an anti-bonding interaction, and thus there's no electron density there.
So does it take away from the bond?
We can sort of draw this out. This sort of has interaction all the way across. If I try to draw this out a little bit better, we're going to have sort of, I'll draw in the p orbitals. Okay, we got interaction here, and we got interaction here. But between the middle, there's no electron density. It got canceled out because the atomic orbitals were out of phase and they canceled. So there's no electron density there. So that's what this is supposed to be. Now we can also say, we can actually draw a line through here. And this is called a node. A node is a plane where there's no electron density. Now, as we go along, we'll see more of this. Right now, I'm just sort of spelling it out. We'll try to. Importantly, though, what's the net here? A bonding and anti-bonding will sort of net cancel each other out. And what are you left with?
One.
Yes, this is one bonding net. So it's still called a bonding molecular orbital, but it's not as good as this. This is sort of how we categorize it. Okay, what's another way for these to combine? Well, let me give you this little tidbit of advice. As you go up, the number of nodes increases. How many nodes does this have? Is there a plane or there's no electron density? No, there's 0 nodes. 1 node. Guess how many nodes this is going to have? 2 nodes. That helps you do the next point. Since there are 2 nodes, they're always going to be symmetrical. It's going to come right through here. Now we can see if this is plus, what are we going to draw here? Minus. The node helps us realize that. Since that's minus, what is this going to be?
Minus.
Good. How did you know that?
Because there's this line.
Because there's no node between here, and so that means they're interacting good. So they got to be the same phase. And what's that going to be? Plus. There you go. The nodes helps you draw the orbital phases.
So would you say that's a negative one bonding?
All right, you're already ahead of me. Right. Good. What's the net here?
No.
Anti-bonding. What's the net here? Or what is this here?
Anti-bonding.
And what is this here?
One.
That's bonding. What's the net? AB cancels B. What are you left with?
Minus
1 AB net. So this is an anti-bonding molecular orbital. And there's actually a fourth one. The fourth one is going to be, I'm out of room up there. Maybe you got some room on your paper. How many nodes is the fourth one going to have? 3. Boom, boom. I mean, I'm going to draw it like that, but they're all kind of symmetrical. If this is plus, what is this? Minus, what is this? Plus, and that is, what are the interactions?
All AB.
All AB for a net of what?
3AB.
Yes. 3AB net. That's the worst. That's actually where there's no good overlap anywhere. That's a bad MO. Okay. Your energy, there's always going to be energy line that cuts symmetrically through here. Those that are below the midline are going to be bonding molecular orbitals. Those that are above the midline are going to be anti-bonding molecular orbitals. That's the MO setup. Let's don't forget about the electrons. How many electrons in this compound? Okay, pi electrons. Whenever we do MOs, we're only doing pi electrons. How many pi electrons? 4. Put the 4 in, just like you would do in any standard, what do you call it? Hotel diagram. What do you call it? Electron configuration. Where's your first electron go? Aufbau principle tells us it goes where? It goes there. Where's the next one go? Feel this, but opposite spin. That's Hund's rule. We did not have a degenerate one there, so there's not another one to fill before we start pairing. And then when we pair with opposite spin. Okay? Each MO is going to get 2 electrons. That's 3. 4. All right, that's 2. 3 and 4. There's an MO diagram for butadiene. What does it tell us? Your 2 bonding molecular orbitals each have 2 electrons. That means there's 2 electrons spread out in here. But you say, hold on, there's 4 orbitals. See, that's where you got to remember. This is no longer 4 discrete orbitals. It's now 1 molecular orbital that just looks like this. And each orbital contains 2 electrons. 2 electrons sit in here, and they're spread out all the way through here. Another 2 sit in this type of orbital. We didn't draw the original here, but sit here. It's not as good as that one, but there we go. This is sort of the MO theory. One thing this gives us, remember when we did UV vis? What's going on in UV vis? Electrons get excited. Okay, excited to what? Higher energy what? I mean, if you just look at this, with MO, what happens is, one of these electrons gets excited to the higher energy molecular orbital. So now we can discuss UV vis. By the way, what do you want to call this level? This is the level that's the highest occupied molecular orbital. What do you want to call that? It's your HOMO. Highest occupied molecular orbital, right? What do you want to call this one up here? LUMO, which means lowest unoccupied molecular orbital. Now we use those terms in UV vis, right? Okay. If you go back and look at that, I showed you some here in the HOMO to LUMO gap. That was really I was showing you molecular orbitals there. Now we're able to excite an electron to a higher molecular orbital, and that's what happens in UV vis. And it's hard to discuss that when you're just doing an atomic orbital view that we've always done. All right. Now let's do an MO of benzene. There will be some differences here. Again, I'm trying to go through this pretty quickly. Most of this is you're going to have to kind of work with it. You're going to have to do some reading. We need to make some time because we lost last Friday. You'll also, in one of the handouts, there's a guide to drawing MO diagrams. I think it's the one that you printed yourself. Is that right? It's called the Key to Drawing MO Diagrams. Okay. Let's try one for benzene, though. All right, wait. How do we do this? Let me start by drawing here. We're dealing with p orbitals. We got 6. Pretend there's p orbitals all there. I'm going to draw the phase. What's the best way these 6 could combine? All plus. Might leave some room because I'm going to go higher. Okay? I'm not going to be able to do it here, but on your page you're going to leave some room. Positive all the way around? Yes. And that would give us, way down here. What's the bonding net? 6 bonding net. Good. I'm just going to redraw that down here. How many nodes did that one have? 0. Good. Okay, let's do it again. Now let's try another combination. How many nodes is this level going to have? 1. Draw a node right here. If this is plus, what is this? And this? This? Very good. What do we got here? Bonding, 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 bonding. But what do we have here? Anti-bonding in here. What's the net here? 2 bonding net. 2 antibondings cancel 2 bondings. You're left with 2 bonding net. That's not as good as this one. So in terms of energy, it's higher in energy. We're going to put it up here. Well, guess what? Because it's cyclic, there's another way to draw one with 2 bonding net. There's another way to draw one with just 1 node. That is, we can put the node right through here, actually right through 2 carbons. If this is plus, what is this? If this is minus, what is this? Minus. And here, there's no electron density on 2 carbons. Where did that get you thinking? What's the net here, T? That's bonding, and what is this? This is nothing because these are not next to each other. So they're not interacting out of phase to make antibonding. They're not interacting at all, so it's just nothing. What's the net there? 2 bonding net, just like this. So they have the same energy. What do we call orbitals that have the same energy? Degenerate. Okay? It's because of the cyclic nature that we can have degenerate orbitals. Okay. The midline is going to come. How many total MOs are we going to draw? We haven't said this before. 6. Here's how you answer that. How many did we draw for butadiene? 4. It had 4 p orbitals, so we drew 4 MOs. This has 6 p orbitals. Guess how many MOs? 6. What if it had 12 p orbitals? How many would you draw? Yes. Basically, however many you combine, that's how many you're going to produce. Okay, the next one, I'll go up here. How many nodes? 2. Let's do here and here. If this is plus, what is this? Minus, what is this? What is this? See, that has to be no interaction here and no interaction here. What is this? Okay, what's the net?
Two antibodies.
2AB.
I'm getting a little congested here. Indeed, it's 2AB net. 2AB net. I want to finish this up before we dismiss. There we go. Now the midline is going to come right through here. Because now we're doing antibonding net. Well, guess what? There's another way to draw one with two nodes. We can come right through here, I believe, and right through here. No, that's not it.
Do you just draw the X directly through the carbon?
Does that give how many net? Oh, this actually works. Yeah, sorry. So this is, if this is plus, what is this? If this is plus, minus. And nothing here, that's it. What is this net? That's 2AB net, and so it's also here. Let's look at the final one. It's got 3 nodes. I think it goes boom, boom, and boom. I believe if that's plus, what is this? I mean, what's the net there? 6AB net. Because if you look, every interaction is AB, and there's 6 AB interactions. There's no bonding. So that's up here. That's 6 AB net. There are your 6 MOs. How many electrons we're dealing with? How many electrons in the pi system? 6. 1, 2, 3, 4, 5, 6. There's your 6. What do we see? All electrons are in bonding molecular orbitals. We'll summarize next time. And importantly, all electrons are paired. Please try to do an MO for cyclobutadiene. There's directions with the key. And we'll look at butadiene, cyclobutadiene next time.
That was the square, right?
That was what?
The square?
Yeah, cyclobutadiene. It's a square shape. We'll summarize this on Friday.